homology session. The first speaker this afternoon is Charles Rezk from the University of Illinois at Urbana-Champaign. Charles got his PhD in 1996 from MIT and has held both a Sloan Fellowship and an AMS Centennial Fellowship from 95 to 96 and from 99 to 2000. Charles will speak about isogenies, power operations, and homotopy theories.
Thank you. Thank you for the opportunity to speak here. I would like to talk about something that's been a large focus of what I've been thinking about over the last decade. I've given this title, Isogenies, Power Operations, and Homotopy Theory. It's an interesting, it's motivated by understanding certain features of certain generalized cohomology theories, and it leads into an excursion into some arithmetic algebraic geometry. I'm not a native speaker of that subject, so I always feel like I'm groping in the dark trying to understand how to talk about these things. So, there we go. Here's a quick plan. I'll tell you what I mean by power operations. I'll do this using a very classical example that's easy to explain, namely power operations in K-theory. You'll see exactly what I mean there. I'll go on, and the main body of the talk will be a discussion of power operations in something called Homological theories. I'll have to explain what they are, and I'll tell you what we know now about the structure of these operations. And then I'll give some applications, which include actual applications to homotopy theory. So there will actually be topology in this talk of some sort. I realize this is probably not as much topology as other talks in this section. I'll do my best. So I'll take as my template example, or motivating example will be a K-theory. So Grothendieck first defined K-theory in the algebraic context. K of x, x is for him a variety, or later formulations is a topological space, say a compact Hausdorff space. K of x is, you take the collection of isomorphism classes of vector bundles. Actually, I should have probably written the free abelian group on the collection of isomorphism classes of vector bundles over your space, modded out by an equivalence relation. So in Grothendieck's case, an extension is converted into a sum. So if you like topologically, K-theory is essentially stable equivalence classes of vector bundles. I'll think of complex vector bundles. Now the observation which came right at the beginning of the subject, when Grothendieck was thinking about this as a context for formulating the Grothendieck-Riemann-Roch theorem, was the observation that natural operations on vector bundles give rise to natural operations on K-theory. So the obvious one is the tensor product of vector bundles. I've already talked about direct sum. That's used in the definition of K-theory. Tensor product of vector bundles defines a product on K of x. K of x is a commutative ring. But there are additional operations, for instance, the exterior power of a vector bundle, some power n. Take a vector bundle, you get lambda n of v. That induces an operation on K of x, which is also called lambda n. It actually is compatible with this equivalence relation. Likewise, symmetric powers. In fact, there's an infinite list of things you could define of this nature. So K-theory takes values in some fairly carries some complex structure, complicated structure, which is encapsulated by saying that K of x is a lambda ring. This definition is also due to Grothendieck. So Grothendieck defined a lambda ring to be a commutative ring together with a bunch of functions, lambda n for n greater than or equal to 1, satisfying a list of axioms, which I've not decided to reproduce here. The axioms basically say things like there's a formula for lambda n of a sum, and that's some polynomial on the exterior powers of x and y. That formula is actually a familiar formula for the exterior power of a direct sum. But there are also formulas for the exterior power of a product, meaning the tensor product, or even for the composite of exterior powers, exterior power of an exterior power, in terms of polynomials in exterior powers of the inputs. Those formulas are not really easy to write down in closed form. Usually you write them using some symmetric polynomials to create a generating series that describes those formulas. So it's a fairly complicated piece of algebra that describes the structure on K of X. So later on, Atiyah realized you could put all of this into the context of equivariant K-theory. So now if I think about a compact Lie group G, say, acting on a space X, I can define the equivariant K-theory. It's just the same definition. I'll look at equivariant vector bundles on X, mod out by the same equivalence relation. You're going to use the notation a few times here, K of X mod G for equivariant K-theory. I guess that implies that somehow it's really an invariant of an orbifold, in this case X, the translation orbifold of G acting on X. That's just notation. So the observation is, well, the tensor power of a vector bundle, the n-fold tensor power, carries extra covariance. Obviously, it has a symmetric group action. So an action by sigma n, the symmetric group on n letters. And so it defines a function from kg of x, the G-equivariant K-theory of x, to the equivariant K-theory of G times sigma n. The extra covariance is entirely in the vector bundle. And, well, it's a simple argument that that's really the original kg of x, tensor the representation ring of a symmetric group. Which, of course, we understand pretty well because we understand representations of symmetric groups, of the complex numbers. So one way to think about this is that the theory of lambda rings encodes lots of information about the representation theory of symmetric groups. This has been exploited by people with symmetric representation of symmetric groups. All right, so lambda ring structures, it's complicated. There's all these operations. They're not additive. They satisfy some crazy formulas. But it was early understood that you could really work with them. One formulation of how this works is due to Wilkerson. The observation is that if you take a torsion-free commutative ring, so as an underlying abelian group is torsion-free, to put a lambda ring structure on that ring, you're really just putting a bunch of ring homomorphisms. In fact, for every prime, you'll choose a lift of the Frobenius, p power, which is a ring endomorphism R, and these endomorphisms should pairwise commute for different primes. These psi p's, as I call them, are well known. They're the Adams operations. So they were actually introduced by Adams in the 50s. There's an Adams operation for every n. A feature that I'd like to point out is they satisfy congruence. The pth Adams operation for a prime applied to an element is congruent, not equal, but congruent to the pth power of that element, not p. That's the observation that it's a lift of the Frobenius. In fact, any lambda ring has not just psi p, it has another function called theta p. Theta p, so psi p is a ring homomorphism, theta p is just a function, but you can think of it as something that witnesses this congruence. So not only is psi p of x congruent to x of p mod p, but there is actually a canonical element that witnesses the congruence. And that's called theta p. That's a natural function on lambda rings. So this was one set of properties of lambda rings I wanted to point out. I pointed this out because it will show up again, an analogy of it will show up again when I talk about Moravia E-theory. Here's a second property of lambda rings, which is very useful for calculating things in K-theory. It's well known to people who have ever thought about this. If you take a line bundle, complex line bundle, let's say, over X, if you want to compute the Adams operation, that has a very simple formula. The Adams operation applied to a line bundle is the tensor power of a line bundle. It's another line bundle in particular. Now I want to connect what's going on here to some kind of geometry, in the sense of algebraic geometry. So I want to talk about GM, which is the multiplicative group scheme. So I'm going to think of the Laurent polynomials over Z. And that scheme is actually a group scheme because the Laurent polynomials are a hot algebra. Now this ring, the Laurent polynomials, is actually the representation ring of U1. Complex representations of a circle are direct sums of powers of tensor powers of the canonical representation. So the representation ring of U1 is this ring, and well, it's the multiplicative group. So somehow that is associated with K-theory, the multiplicative group. The Adams operations, remember, are ring homomorphisms on the K-theory, in particular on this representation ring. And in fact, they're actually automorphisms of the group scheme. They're isogenies of GM. So they actually define homomorphisms of the multiplicative group scheme to itself, which are, in fact, the multiplication of the nth power map. When I say that GM is a group scheme, I just mean that it's a, if you like if you have a ring R, the R points of GM are just simply the units inside the ring R. Brackets n is the function that takes a unit to its own nth power. That just encodes the fact that psi n of t is t to the n. So there's this funny connection that it looks just, I pulled it out of thin air, what does that have to do with anything? But it will, when we see the analogy to Moravi theory, this is sort of what we're trying to generalize. Isogeny means a finite and flat homomorphism of group schemes. So to make another remark, instead of thinking about equivariant K-theory of U1, I think about the Borel equivariant K-theory. So I think of K of the classifying space of U1. Classifying space of U1 is also the infinite complex projective space. That's not a scheme, it's a formal scheme. It's not a group scheme, it's a formal group scheme. It has a group law in the sense of formal geometry, and it's the multiplicative formal group. So I've listed these two properties about Adams operations and how they act on line bundles. And they were both discovered by Adams in the 50s, and they were crucial to some of his great results that he found. For instance, for his solution of the vector fields on Speeder's problem. He invented these precisely to solve that problem. Now, so that's a discussion of power operations in K-theory. So they're operations on the cohomology, this cohomology theory, they're natural operations. You saw that they actually arose from something very explicit involving the nature of cycles in the theory. A cycle in K-theory is a vector model. That's what represents K-theory classes. Other generalized cohomology theories admit power operations. So if you have a general cohomology theory, lowercase h star, let's say it takes values in commutative rings. To have power operations means, in particular, you have some kind of operations, which are here called Pn, which go from h star of x to h star of lower sigma n of x, by which I mean here the Borel equivariant cohomology of x with respect to the group, the symmetric group, which simply means the cohomology of x times the classifying space. You would like to have functions that refine the nth power map. So cohomology is a ring. You would like these to refine that. And that's what a power operation is. It is non-trivial to construct power operations. They need not exist. This is extra structure in a cohomology theory that does not come for free. They do exist if you know that your cohomology theory is represented by what I've called here a structured commutative ring spectrum, which is just a catch-all term for various notions of commutative ring spectra. So a spectrum represents a cohomology theory. Commutative ring spectrum is a spectrum with multiplicative structure. There are several models for what a structured commutative ring spectrum is. Sometimes they're called commutative S algebras or E-infinity ring spectra. I don't want to get into a discussion of what all those means. They're all known to be equivalent ways of equivalent information. So here are some examples. So the original example, in fact, is not K-theory. It's ordinary cohomology. If you look at ordinary cohomology with coefficients in a finite field, Steenrod introduced natural operations, which are the Steenrod reduced powers, the Steenrod squares they're called if you're over F2. Those are power operations. In his original construction, that's not obvious, but he gave a later construction that works at every prime, which is in fact analogous to what I described for K-theory. It involves the use of the symmetric group. It's probably worthwhile noticing that you can take this formalism and move it to other contexts. So when Vygotsky introduced used features of motivic homology theory to prove some famous conjectures, part of that involved constructing analogs of Steenrod's operations. And the construction of those operations is in fact precisely analogous to what Steenrod does. Merely more difficult in a more general context. It's exactly the same thing. Another kind of power operation was introduced, I think, by Quillen. This is the earliest example I know. If you take a Bordism theory, cobordism, with respect to U or SO, there are kinds of power operations on these theories. Borism theories, the cycles are given by manifolds, because Borism classes are really important elements in the theory are represented by Borism classes of manifolds. And the power operations correspond to a geometric construction where you take the nth power of a manifold, Cartesian power, and think of it as an equivariant object with an axiom of symmetry. He used these to prove that, he gave one of his proofs that MU, the homotopy groups of MU are the Lazard ring that classified forming group roles, was given using this technology. So the idea I want you to get here is that sort of if you have a generalized cohomology theory that sort of comes from some geometric, has some natural geometric representation, like K-theory has vector bundles, Borism comes from manifolds, the symmetries in the sort of that geometric or data or whatever somehow lead to having power operations. This is sort of the picture you tend to expect. If you have a cohomology theory that comes from nature, it should have these power operations. In all these cases, it's a very useful structure to have. I didn't even, well, Steenrod squares are crucial to all calculations of homotopy theory, for instance. I'm actually interested more than anything in what's called elliptic cohomology. This is not a talk about elliptic cohomology, so I don't want to go into great detail. Elliptic cohomology is something that sits in an analogy with K-theory. So K-theory has something to do with the multiplicative group. Elliptic cohomology has the same sort of thing to do with elliptic curves, or with an elliptic curve. There are multiple elliptic cohomology theories corresponding to different elliptic curves. K-theory geometrically has cycles, which are vector bundles. Elliptic cohomology geometrically has cycles, well, I don't know what they are. They're supposed to be something like two-dimensional conformal field theories or something of that nature. Graham Siegel propounded this. Lots of people have worked on this, and lots of partial results on the connection between elliptic cohomology and these things, but you don't really have a geometric construction of this theory. Here are some examples. One, which may show up later, is called TMF, the topological modular forms. This is the elliptic cohomology associated to the universal elliptic curve, which lives over the moduli stack of elliptic curves. It has a nice feature. It's a structured commutative ring spectrum in the sense of the previous slide. So it has power operations. There are also equivariant elliptic cohomology theories. Jacob Lurie has given the most general construction of such theories. It's an open question as to, does elliptic cohomology theory admit power operations? Or actually, I think it's a better question, which equivariant elliptic cohomology theories admit power operations? There are elliptic cohomology theories associated to various different elliptic curves, and I think only some of them should be expected to have power operations. So for me, that's a motivating question. I won't really show up in the talk, but I just thought I'd point that out. I do want to show an example that's non-trivial that illustrates sort of a non-trivial theory of power operations associated to elliptic cohomology. It's a very nice example. It's really worth thinking about. So there's an elliptic cohomology associated to the Tate curve. The Tate curve is, well, often people say it's C star over Q to the Z. You take C complex units, you divide by the integers generated by some parameter Q, more or less than 1. In fact, that would define a complex curve. In fact, Tate observed that this was actually defined integrally by some explicit formulas. There's an equivariant elliptic cohomology at the Tate curve, which pleasingly is really a kind of equivariant K-theory, more or less. Equivariant elliptic cohomology at the Tate curve is really the K-theory of what's called the ghost loops of X acted on by G. So L means the free loops, mass of a circle into X. Ghost loops are constant loops. Constant loops in a space are not very interesting. They're just points in the space. But if you have an orbifold, then a constant loop turns out to mean something that an orbifold turns out to be, well, you have a path, but it's an orbifold, so you get to move around by elements of the group. So you get to jump by an element of the group. So a loop in an orbifold is somewhat more rich object. And even if you have a constant loop, it turns out to be somewhat non-trivial. So the Tate elliptic cohomology is really the K-theory of the ghost loops. The object on the right-hand side is something called twisted sectors. That's a terminology from mathematical physics.
Is this the thing that's sometimes called the inertia stack?
It's related to it.
It's related.
the U1 that's present there makes it a little bit richer. Ganter observed that this theory has power operations. In fact, the structure of power operations, you can actually spell exactly what it means. In particular, you have not just the lambda operations, because after all, it's kind of K-theory. You have a second family of operations, which I've called mu. These satisfy some identities. You can call these the structure of an elliptic lambda. My student, Jen Wanis, has proved that this, in fact, is the entire structure of power operations on elliptic tape, elliptic cohomology. So it's actually interesting that the lambdas are the usual K-theory operations. The mu's come from doing something very naive, which is reparameterizing loops. If you have a loop, you can run it m times as fast. And that's how you build that operation mu. So it has a completely geometric interpretation. Nonetheless, that's the complete story of power operations. Okay, so that's just an introduction. I want to talk about the example of Morava E-theory. I don't know, Morava E-theories don't really seem to come from nature. So I might not confuse the term designer cohomology theory for these. They're manufactured artificially using the techniques of homotopy theory. It's a little bit wrong to say they don't come from nature. Two examples of Morava E-theory are completions of some things that do seem to come from nature, like K-theory, completed at a prime, is an example of Morava E-theory. Another example is elliptic cohomology, completed at a supersingular curve. That's another example of Morava E-theory. These theories have a rich theory of power operations, which I'm going to tell you about in a minute. So I'm going to tell you what these are. And so the moral here, or the slogan, so for K-theory, what was the story? There was this fancy notion of a lambda ring geometrically comes from exterior powers, vector modes, whatever. But we could understand that, well, if we forget torsion in our ring, it's just given by these Adams operations. And the Adams operations are essentially correspond to isogenies of the multiplicative. So up to some fiddling around, or up to some details, the power operations are controlled by the isogenies of GM. And so the slogan here is that power operations for Morava E-theories are controlled by deformations of Frobenius isogenies of one-dimensional formal loops. I'll have to explain what all of this means. That's the slogan for this section. All right. I'll explain later some of the terminology on this slide. I'll put it out. So I'm going to start with a formal group, one-dimensional commutative of height n, so finite height over FP, let's say. Then, first Morava showed there was a cohomology theory, and then Gorski-Miller showed that it's actually represented by a structured commutative ring spectrum. This cohomology theory, E sub G0, is associated to the formal group in the following way. It's complex orientable, and its formal group is the universal deformation of G0 in the sense of Lubin Tate. I'll say what this means in a future slide as well. This theory, like any cohomology theory, has a coefficient. The E cohomology of a point is a power series ring over ZP, n-1 generators. And it's even periodic. It also has a guaranteed degree 2, just like K-theory, because K-theory is even periodic by Bach periodicity. Okay. So let me go back a little bit. So a formal group, it's an object in formal algebraic geometry. It's locally described by a formal group law. So a formal group law is simply a power series. Formal group law over R is our commutative ring, is a power series in two variables satisfying these identities. Effectively, it satisfies the equations for an abelian group, unit commutativity and associativity. For future reference, I'm going to use this notation brackets P of X as the P series. It's what happens if you add X to itself at P times in the group law. Complex oriented cohomology theories are cohomology theories which take values in a ring, which have a relation to a formal group law, in the sense that the cohomology of infinite complex projector space is a power series ring on one generator X, which restricts to the fundamental class of CP1. So examples include ordinary cohomology, K-theory, elliptic cohomology, and the Morava theories. The feature of these is that the X here you think of as providing a characteristic class for complex line bundles. And the group law is giving the formula for that characteristic class applied to a tensor product of line bundles. So for ordinary cohomology, the characteristic class is the first Chern class, And the law for the first train class of a tensor product is addition. So ordinary cohomology is associated to the additive form of group law. K-theory is associated to the multiplicative form of group law, and so forth. All right. So I'm going to start with a formal group of height n over fp. So this means its p series has leading term of power x of p to the n. And now I'll consider a complete local ring whose residue field is characteristic p. I'm going to define a groupoid called def0g0r. These are deformations of G0 to the ring R. The object, which is a deformation, is a pair consisting of a formal group over R, together with an isomorphism of formal groups between G0 and the restriction of G to the special fiber, to the ring, to the residue field R mod n. So that's an isomorphism of formal groups over R mod n, not over FT. So I'm going to choose a formal group over R, and then there's an identification of the special fiber in the language of deformation theory, identification of the special fiber with G0. And I'll make this a category by including isomorphisms of deformations. So these are maps or isomorphisms of formal groups which are the identity of the special fiber. Okay, so this is some notion of a deformation of a formal group. And Lubin and Tate classified these up to isomorphism. In fact, they produced a universal deformation. The universal deformation is defined over this rings of P adjoining A1 through A minus 1. And Moravec E-theory is characterized as being the cohomology theory, complex-oriented, whose formal group is the universal deformation of G0. So there's in fact a Moravec E-theory for every G0. Isogenies of formal groups. Well, I'm going to enrich this def0 by putting in morphisms that aren't isomorphisms. So isogenies are homomorphisms which are given locally by some power series, which have some leading terms of invertible, c invertible times x to the n. So I'll say it as degree n. Any formal group over fp has a distinguished family of isogenies, which are given by the Frobenius. So they're given by the formula, which is the p to the rth power map. That's from R. And so now we'll have a category of deformations of Frobenius. The objects are the old objects, deformations. The morphisms are going to be homomorphisms or isogenies of formal groups, which on the special fiber are Frob R, or some power Frobenius. That includes the isomorphisms that I had before. That's when R equals 0. All right. Now I have for every ring R a category of deformations of G0 to R. And I can also pass between rings by a local homomorphism. I can have a functor. All this data, this is all already getting kind of complicated. I'm sorry for that. We'd probably call this a stack, some kind of attic site. It's associated with some kind of category of fiber groupoids. It talks about stacks. But it's not a groupoid. Def R is not a groupoid, it's just a category. So sometimes we've been using the language pile for these objects. There doesn't seem to be a good name in the literature for what this is. They're often called just stacks, again, but stacks in categories or categories fibered in categories. We call it a pile. But it's like a stack. Finally, I'll give a notion of sheaves on def. So what this will be an association for every complete local ring R. I'll give a functor, a sub R, from def R, the deformations to R, to the category of R modules. Since I'm doing this for every ring, it should be compatible with maps between rings, the local homomorphisms. So it'll be an isomorphism relating AR to A of R prime. And more so, I say AR extending to R prime and A of R prime. And that's actually part of the data. It's the definition of sheaf of modules. And there's a similar notion of a sheaf of commutative rings. Okay, this is, play this game of defining a very fancy category. In the end, so I'll denote these by mod def or com def, sheaves of modules on def or sheaves of commutative rings on def. In the end, mod def is some abelian category. In fact, it's isomorphic to some category of modules over some associative ring gamma. So effectively, this is a very complicated game for coming up with some particular associative ring gamma. So this is sort of how I think of, in practice, it's just a, I'll show an example of gamma in a little bit. So the key observation is that Moravec E-theory takes values in sheaves on def. So power operations, the structure of power operations make Moravec homology, which ordinarily takes values in graded commutative rings over the coefficient ring of the theory, with E star of a point. We can lift this to a functor from E star from spaces to graded sheaves of commutative rings on def. I'm not going to describe why that's true, but remember, power operations had something to do with the symmetric group. For E-theory, they have something to do with the E-cohomology of the symmetric group. And so I'll just point out the key step was given by Neil Strickland, where he identified a certain quotient, the cohomology of symmetric groups mod, a certain ideal, as the object that classifies subgroups of deformations, subgroups of a given rank. That's the key technical result that makes this good. There's a broader context here. I don't want to take too much time on this. I've stated a result in terms of a cohomology that takes values and things. But in fact, the structure that we're using is not E star of x. This is actually a structure that lives on the cochains. So if I have a space x, I can build a spectrum e to the x plus. We call it the cochain spectrum e. And the E cohomology is really the homotopy groups of that cochain spectrum. And the real theorem is that it's actually the homotopy of this cochain spectrum that carries these power operations. So the cochain spectrum turns out to be what's called a K-and local commutative E algebra. And what the theorem really proves is that homotopy groups, the K-and local commutative E algebra, the functor of homotopy groups actually lifts to this category of com star def. All right. So there's this fancy algebraic category that's the target of taking homotopy, or if you like, of taking the E-cohomology of space. So this is the objects in this category carry all the operations that we'd like to find. Now the thing I said before was that this fancy category of modules on def was just modules over some ring. So what is this ring? Here's two examples. In the height 1 case, the easiest example of a height 1 formal group is the multiplicative group. Its Moravec E-theory is complex K-theory completed at the prime. The ring is a polynomial ring on one generator, or ZP. The generator is the atoms operation, psi p. So I recover part of the story that I actually had for Equivariant K-theory. I recover the pth atoms operation. And that's it, that's the ring. At height 2, we can calculate some things. The reason we can calculate some things is that there's a source of formal groups coming from elliptic curves. So for instance, I'll take a supersingular elliptic curve over F2. Elliptic curve is a group scheme. It can be completed at its identity element. We get a formal group. And therefore, we can plug into this machine. And we can actually describe what the ring gamma is. So I just wrote out in formulas. This is not actually a very useful presentation of the information, but it just illustrates that there's actually, you can actually compute with this. So for instance, on Z2 adjoining a power subring A, that's the coefficient ring of this E-theory. And then there are three non-commuting generators of this ring, Q0, Q1, and Q2. I wrote down two sets of relations. There are relations that relate the QIs to the scalars. The coefficient ring Z2 adjoining A is not the center of this ring. It's the first two relations. And then the second two relations are more interesting. They relate the QIs. They're quadratic relations. There's a similar description that we know at the prime 3, and it should work at any prime, which can be used explicitly if you want to. Mod a prime, you can describe these uniformly at height 2. So gamma mod p, there's actually a formula for it at all primes. In all these cases, all these calculations actually use things we know about elliptic curves. Let me list a few interesting properties of this ring. So for any G0 of finite height n, we have a ring gamma. The first observation is that the center of this ring, the associative ring, its center is a commutative ring on n generators. It's a kind of Hecke algebra. In fact, well, just that. Here's a more interesting structural feature. The ring gamma for any situation is quadratic. It's a ring that contains the coefficient ring, which is pi star of E0, pi star of E rather. It's a tensor algebra on a certain E star bimodule. Mod a certain set of relations which live in the second tensor power. So it's generated by some relations, and then, sorry, it's generated by a set of generators, and then it has relations that are quadratic. And this is a standard feature of this ring. That's actually a consequence of a better result. It's not merely that ring is quadratic, it's actually Cazul. So quadratic rings, in some cases, are Cazul. That is, they admit canonical, or they admit small homological presentations. So in the case of gamma, there exists a bimodule resolution, gamma-gamma bimodules, of an explicit type. So this involves some modules called CK. Each CK is finite and free over E0. There's a direct relationship between C1 and C2 and the generators and relations in that algebra. Notice that this resolution has a finite length. So, in fact, we learned from this that the ring gamma actually has finite homological dimension, 2 in it, given the length n of this resolution, and E0 also has a dimension n, which gives you 2 in it. I'm running a little bit slow, so I don't want to take too much time. It's an interesting feature of the proof of this. I don't want to go into detail. It was conjectured by Ando, Hawkins, and Strickland when they were thinking about power operations. It's really a theorem about formal algebraic geometry. You have a formal group, and, well, you construct this weird category, which is ring, the feature about the homological features of this category. But the proof I know is topological. It actually uses the relationship between this formal algebraic category and the Moravi E-theory. So gamma, it turns out, is related to the E-theory of symmetric groups. So it's easier to describe in terms of the E-theory of the E-homology of symmetric groups. It's the primitives in this hot algebra you get between the direct sum of the E-theory of the symmetric groups. If you take iterated Reith products and take the primitives inside that object, that gives you the bar complex. Finding a Cazul complex really means splitting off a small piece of the bar complex. And observing that gives you, that you can use that as a resolution. And so you do that using this topological description. Iterated Reith products of symmetric groups are in fact symmetry groups of chains, certain kinds of chains of partitions of finite sets. Partition is an equivalence relation, so you look at a chain ordered by refinement of partitions, that has a symmetry group. Some of them, particularly symmetric ones, there's a symmetry group of Reith products. And so you can actually relate the calculation you need to do to something about the Verdon homology of partition complexes. Partition complex is the nerd of the poset of partitions of a finite set. So it's kind of curious. I really think this is not supposed to be a deep theorem about formal groups. It should have some formal proof. I don't know it. In the height 2 case, you can give an algebraic geometric proof using facts, known facts about the moduli of subgroups of elliptic curves. So in that case, we do an algebraic geometric proof. All right, a couple of features. There's a congruence criterion. So I showed one for lambda rings. So lambda rings, there was a complicated category of lambda rings, and the torsion-free objects had a simpler description. Here we go the other way. There's actually a complicated category of T algebras, which is the real target of the homotopy of a K-local community E algebra. I didn't even bother to describe what it is, it's complicated. I don't know a closed form description. But in fact, it's the torsion-free objects in this category that are exactly given by sheaves on COM-def, or sorry, sheaves of great commutative rings on def. More precisely, they're sheaves on commutative rings on def that satisfy a Frobenius congruence. So there's a particular element you can find, Q and gamma, and that element Q is an operation on the Moravi E-theory, and it has to satisfy a congruence. Q of x is congruent to x to the p mod p. It's completely analogous to the Adams congruence I described earlier. I think that's a special case of it. And as with lambda rings, any T algebra carries an operation which is a witness to the Frobenius congruence, or some operation of theta. Witnesses are congruent in the sense that there's a formula, Q of x equals x to the p plus p times theta x. All right. I want to give some applications in the time I have left. I want to mention this one briefly just because it's kind of remarkable that this little fact is actually useful. It turns out that having this witness means you can show that if you have any K-local commutative E algebra, torsion elements in the homotopy are actually nilpotent. It gives you a nilpotent result on the homotopy. Merely the existence of this theta. There's a proof. So Matthew, Noel, and Naumann observed this, and then they combined it with the nilpotence theorem of Devenant, Hopkins, and Smith to prove another nilpotence result, which was conjectured by Peter May. A proof was known to Mike Hopkins, but I don't think he really shared it with the world in public form. But they found a different proof, which is actually much simpler. If you have a structured commutative ring, then the kernel of the Ravitz map from the stable homotopy to just the ordinary homology with integer coefficient always consists of nilpotent elements. It's a very strong result. Now I'll describe here two applications. I'm going to skip this page. We were motivated by, well, the motivation for this was our work that they did with Matt Ando and Mike Hopkins to show that topological modular forms, one of these versions of elliptic homology, admits an orientation by the covariance theory associated to the string group. This is a realization of what's called the Witten genus. The particular way that role that this power operations get involved is the construction of something called the logarithmic operation. So there's a spectrum. Let's go back to the previous page. There's associated to a structured commutative ring. There's a different spectrum called the unit spectrum. It's analogous to taking a commutative ring, then you take the additive group of units. It's a Wheeling group. Well, if you have a structured commutative ring, there's associated to it a spectrum, which is its group of units. It's called GL1 of A. A logarithmic operation is just any spectrum map from GL1 of A to A. One example was constructed by Tom Dieck in the case when A was P-complete K-theory. There's a logarithmic operation going from the units of P-complete K-theory to K-theory, and he wrote down a formula. That's how he gave it. Here's the formula for his logarithm. It's defined in terms of the P-Adams operation, psi p, and in terms of log, which is just the usual Taylor expansion of the logarithm at 1. The formula I've just written down here actually doesn't make any sense because it doesn't converge. But I could rewrite it formally, put everything inside the logarithm, and remember that there's a Frobenius congruence. The P-Adams operation is congruent to the P power mod p, which means that the thing inside log there is congruent to 1 mod p. And the expansion of the natural log actually converges for p-adically for things that are congruent to 1 mod p. You can even expand this out in terms of that witness theta. There's a formula for the Tom Dieck logarithm. So the result is that you can generalize the construction of this logarithm to any Moravec theory. Essentially what you do is you write down the easiest formula you can think of that generalizes Tom Dieck's formula and has a chance of working, and it turns out to work. And this turns out to be the formula you get. There's just a logarithmic operation. Its formula involves, it's a sum of some terms which involve these Heck operators that I described on the previous page, these particular power operations within the center of the gamma. This was motivated by proving this result about the Witten genus, but I'm going to pass by this slides behind time. Let me briefly describe one more application. So if I have a commutative ring, and I have a K and an augmented algebra over K, well, the augmentation is giving a point, and then I can let Q sub K of R be the augmentation ideal mod the squared. In terms of geometry, this is the cotangent space. And then I'll take the dual of that, and I'll call it the tangent space. In structured commutative rings, there's an analog of this. The cotangent space, which I've called here TQ, is called the reduced topological Algebraic homology of R at the augmentation. And the tangent space is called the reduced Algebraic cohomology. So I'll call these TQ and TT. That's not standard notation. Do that as it may. So here's an example where this shows up in rational homotopy. If you take the rational cochain spectrum of a simply connected finite type space, and you take its derived tangent space in the sense I just told you, its homotopy groups are in fact the rational homotopy groups of the space X. This is actually a theorem of Sullivan because the rational cochain spectrum is just a fancy way of talking about the rational cochain complex. It's a different language talking about the same object, and in the language of a cochain complex rather than cochain spectrum. This was Sullivan's observation. I'd like to point out that if you change the theory, this can act very differently. For instance, Mendel observed that if you take mod P cohomology, the derived tangent space is trivial. Which is interesting because he showed that the p-adic homotopy calculus space can be recovered from the P cochange, but you don't do it this way. So, are there structured commutative rings that behave like rational cohomology, not like mod P homology? One example is K and local structured commutative rings like Moravia E-theory. So on this slide, I'll show the result that Mark Behrens and I have proved, although the write-up is in progress. If I take the Moravia E-theory at height n, and I take as my space an odd-dimensional sphere, then the cotangent, derived cotangent space of that object is not zero. The P cochange on X is not zero. In fact, it computes something that's of interest in local homotopy theory. It's the E cohomology of what's called the Gaussian-Kuhn function applied to X. And I don't want to explain what that is. It just doesn't fit to this talk. I'd like to relate this, though, with what I told you about power operations. So the object phi n of the odd sphere is an object of interest if you're interested in commuting homotopy groups of spaces through the prism of chromatic homotopy. Now, in general, if you have a Moravia E theory, you take any structured commutative ring R that's augmented over E, there's a spectral sequence that computes the homotopy groups of the derived cotangent space. So derived tangent space, TTE of R. If pi star V is smooth as a ring over pi star V, then the E2 term is actually x'd over this ring gamma, over this ring of operations. And so we can apply the spectral sequence in this result, and we get a spectral sequence that computes the E cohomology of this Gaussian-Kuhn function applied to an odd sphere. At the case of height 1, this is known. In the case of height 2, we get a new calculation. Somewhat surprisingly, the spectral sequence collapses at x2. x0 and x1 vanish. I pointed out before that gamma comes with a Cazul resolution. So in fact, all the higher x for s greater than equal to n, greater than n vanishes. So we knew that we only have finite many groups to think about. In fact, we only need 2. So in the last slide here, I discussed some vistas. Since I'm out of time, I'll just point out that this formalism that I described for Moravia E theory makes sense for equivariant elliptic cohomology. The algebraic geometry side of the story makes sense. There's a pile of elliptic curves and isogenies. There's a category of modules that has an analog of this Cazul property. That describes the theory of power operations in known examples of elliptic cohomology where we have power operations. And I'm interested in learning whether this can actually make a theory of power operations for elliptic cohomology in general that has these features. I guess I'll stop there. Thank you for your attention.
Charles. So we're a little bit late, but maybe we have time for one question. Well, if not, let's thank Charles again and the next talk will start 10 minutes past.